Okay, so welcome to this second to last talk of the Parameterized Complexity School. Thanks for those of you who are still here. I can see the ranks are starting to thin. We've approaching the end. You can see that you're approaching the end, right? The ranks are starting to thin. My slides have gone from like beautifully designed PowerPoints to something pseudo handwritingly. Hopefully you'll be able to read things, at least when I zoom in on them, yes. But what this talk is about is that suppose you now have proved that your problem isn't fixed parameter tractable, or it is fixed parameter tractable, but your FPT algorithm is still too slow. Now, you've also proved that your problem is inapproximable in polynomial time, or you do have an approximation algorithm, but its approximation ratio is too high. And then you ask yourself, okay, is there some sort of hybrid? Can I now perhaps approximate my problem in FPT time and getting an approximation ratio that is better than what I could have hoped for doing it in polynomial time? So Merov has been talking about how to do this if you want to design algorithms, but suppose you fail to design algorithms, then there could be two reasons for that. One is that you're not smart enough, and the second one is that the algorithm simply does not exist. And of course we would like to convince at least other people that it's the second reason that it's true. Yeah. So how do you do that? So in this talk, I'm going to be focusing on three problems that you've seen already. Clique, I don't really need to define it, right? But still, you're given a G and a K, and you ask, does G have a K clique? Or in other words, find the maximum set of vertices that are pairwise adjacent. At least try to find one of size at least K. Dominating set you also know, so find a set of vertices such that every vertex not in the set has a neighbor in the set, and make that set as small as possible, preferably of size at most K. And independent dominating set, that is a dominating set that also happens to be independent. So you want to find a dominating set, so everyone who is not in the set has a neighbor in the set, but no two vertices in your set are adjacent. So actually, for this last problem, it's not even entirely immediately obvious that every graph has an independent dominating set. Because once you put some vertex into the solution, it forbids you from putting some other ones. So anyone who can tell me a simple argument that every graph has at least one independent dominating set? Yeah, so pick a maximal independent set. Yeah, so pick a maximal set of vertices that are pairwise non-adjacent. They dominate the rest of the graph, because if they didn't, you could have added one guy to them. Okay, so at least the existence problem is easy. The answer is always yes, but so optimization makes sense. Okay, so what do we know about all of these three problems? Well, they're all W1 hard, and notice that dominating set is even W2 hard. W2 becomes, but I just skip. So whenever I put a number in here, it's going to be 1, even though you could maybe have put another number in there.
You could invent W of 1 for this purpose.
Exactly. Yes. I've also given talks where I just omit the brackets and just say W hard, but then people get angry. So now it seems that for these problems you can't really do anything smart at all. All you can do is brute force, pretty much. But now the question is, how much better can you do if you try to approximate? Yeah. So for clique, you can't do much in polynomial time. There is no n to the epsilon approximation for any epsilon strictly less than 1. For dominating set, of course, there is a log n approximation, and that's also the right answer. You can't go below that. And for independent dominating sets, there just isn't an approximation algorithm with any ratio, basically. Like you can't do little o of n approximation. And we're actually going to, we're pretty much going to show this in today's talk. But then the question is, what can you do when you go to FPT approximation, right? So these problems are hard to approximate. They are hard from an FPT sense. So what happens if you try to approximate them? And sort of the bad news now is that these three problems, you can't do anything interesting even if you try to approximate them, assuming reasonable conjectures. So there's actually still open problems regarding the complexity of their FPT approximability, but it's more really about the computational complexity, like how believable can we make it that you really can't do anything interesting. At this point it is pretty believable, and now the question is really how believable can we make it that you can't do anything. So let me tell you what is known about these three problems, and then I'm going to tell you about a little bit about consequences and some proofs. Okay. So for clique, it was shown just this year by Challersmuck et al. I hope this is a name I have a problem.
One person in the room who should be able to read your slides is you.
Yeah. Well, no, I mean, I think I can read the slides, but I still have problems with pronouncing. Look, my last name is Lokshtanov, right? So like, I botch other people's last name, but I'm also very forgiving of people botching my last name. So I think we're even this way, right? So, okay. So right now we know that there is for clique. So for clique, assuming gap ETH, which if you don't see gap, like and don't read whatever is written on my hand, right? Like if you don't see gap, then assuming ETH, okay, you know what ETH is. It says that you have no alpha of k approximation, so you have no approximation algorithm with factor alpha of time f of k n to the little o of k over alpha k. So in particular, if I put alpha of k to be k to the 0.99, then what this means is that you have no k to the 0.99 approximation algorithm in time f of k times n to the k to the 0.01. Yeah? So in particular, if I put in a constant here. So in FPT time, you basically cannot do anything non-trivial. And in fact, here is a silly approximation algorithm for a clique that runs faster than n to the k time. So suppose I wanted an n to the square root k. So suppose I wanted a square root k approximation of clique in n to the square root k time. I just brute force in n to the square root k time whether there is a square root k clique. And if there is one, I output that. And if there isn't, I say no. And of course, what could happen is that, where are we now? I went, all right, here we go. I have to touch this more often, apparently. All right, so if I have a square root k, if I output a square root k clique, there could be a k clique. So this is a square root k approximation, and I'm running in n to the square root k time. So really, the silly algorithm that I could have done for any value of square root k, the silly algorithm is pretty much the best you can do, assuming gap ETH, and this is a result from this year. For
This is very cool. So for k equal n, this basically recovers the known approximation hardness guarantee for clique in the unparameterized form?
Okay,
Never mind.
okay. Let me not go there. I think the hard instances actually require k to be like arbitrarily small. I mean, there are some. Okay. Ask Passin. He's here. He's one of the authors.
Yeah, so it only works for k, something like n to the epsilon for some small value of epsilon. So it doesn't recover n to
Okay.
1 epsilon.
Thank you very much. It's very cool. Didn't know this.
Okay. So now, assuming gap ETH, so notice that clique is a maximization problem, right? So like a factor k approximation is trivial, just output a single vertex. Dominating set, so here actually for any factor, even more than k, right? Like I could, for dominating set, I could have a 2 to the 2 to the 2 to the k approximation, right? So if there is a solution of size at most k, output one of size 2 to the 2 to the 2 to the 2 to the k. However, in the same paper, Chalers-Mock et al. Showed that there is no f of k approximation in time f of k and to the little of k. So you can't do anything better than the obvious, assuming again gap ETH. Okay, and then the question is, okay, what is this unpleasant gap ETH thing? What happens if?
F depends on alpha or what?
What?
It says no alpha k approximation in time f of k n to the O, little O.
Yeah. So for any approximation ratio, you cannot do anything other than brute force. No, f of k is a function of k. F alpha k, f of k, and
Where does the alpha appear? In the little O?
no, alpha does not appear anywhere.
Okay, great.
Yeah.
So it's what you said, okay.
Yeah. Yeah. Okay. Okay. So this is an extremely strong result, assuming you are happy to accept gap ETH. What gap ETH is, I'm going to speak about later. But if you're not happy to accept gap ETH, what happens if you just believe ETH? Well, for clique, we don't know anything. But for dominating set, there was a great paper in 2016 that says that, well, in FPT time, you cannot constant factor approximate it for any constant. In fact, you can't even fourth root of log k approximate it. Okay? So it's a much weaker inapproximability, but also under a hypothesis that assumes significantly less than gap ETH. Okay? However, just before this school, like November 29th, there was a paper on Archive that obtained the same results that were under gap ETH, but under ETH instead. So this is C.S. Kartik, Lekhanukit. How do you pronounce this? Okay, and Manurangasi, Manurangsi, thank you. There we go. And they get the same super strong inapproximability for dominating set, now assuming ETH instead. And this proof actually doesn't have too much heavy machinery. I was seriously considering presenting this here, but it is heavy enough that you probably want to speak 2 hours rather than 1 or something like this. So I at least I wouldn't dare to try doing this in 50 minutes. Okay. This one, independent dominating set, is really hard to approximate. It was been known for a long time, since 2008, that also you cannot do anything clever. And this one I'm going to show you, and then I'm going to show you. So what I'm going to show to you today is first that there is no reasonable approximation algorithm for independent dominating set assuming normal ETH. Then I'm going to talk a little bit about the gap ETH. Actually, I'm going to talk a lot about gap ETH. That's what most of my talk is about. And then finally, I'm going to show you how to get constant factor in approximability for clique in FPT time, assuming gap ETH. So weaker results than what actually was shown, but with a more accessible proof. Okay, so now we're going to show that for independent dominating set, there is no algorithm that can distinguish between graphs that have an independent dominating set of size at most k, and graphs that don't have an independent dominating set of size infinity. And today infinity is basically like n divided by k or something like this. Yeah. Unless the ETH fails. Okay, so assuming the ETH, so any questions to what we're about to prove, by the way? Okay, so we're dealing with independent dominating set. And what we're going to reduce from is, of course, multicolored k-clique. This you've seen a few times during this school already. So And we know that assuming the ETH, there is no f of k n to the little o of k time algorithm for multicolored cake-leak. So what is this problem? I give you a graph, G, which has been partitioned into k parts, v1, v2, up to vk. And each part is an independent set. And now I ask you, find a clique of size k. Now clearly there has to be one vertex from every part. Yeah. So this is known under ETH not to have an n to the little o of k algorithm. Now, what we're going to do is we're going to show that if there exists an algorithm that, given a graph G and an integer k, either correctly concludes that there is no independent dominating set of size at most k, or outputs an independent set of size alpha k, where I can choose alpha to be as big as I want, then I can decide multicolored clique in the same running time. Okay. So how do we prove this? Well, given a multicolored clique instance, where here I have edges, here I have non-edges, and all of these are independent sets, now I need to create an independent dominating set instance such that even from an approximate solution to that independent dominating set instance, I can infer whether this multicolored clique instance has a k-clique or not. So the first thing I'm going to do is I'm going to just take the complement of the graph. Okay? So all of my edges turn into non-edges, all of my non-edges turn into edges. So in particular, all of my independent sets here, like v1 up to vk, now turn into cliques. Now notice that because we're looking for an independent dominating set, we can now only pick at most one vertex from each of these color classes. If for some reason we wanted to, we cannot pick more than one. And furthermore, we can pick exactly one vertex from each of those color classes if and only if that vertex set is an independent set in the complement of the original graph. So in particular, if it's a clique in the original graph. Okay, so now all we need to do is to incentivize an independent dominating set to pick one vertex from each of the color classes, and we can really incentivize it by adding something that I call guards. So what are guards? I just make, for the color class, say v1, I'm going to make an infinite number of vertices that are independent among themselves and see v1 and nothing else. Okay? So I put some guards on v1, I put some guards on v2, v3, up to vk. Now, notice...
And they see all their apexes for every v1.
Yes, so these guys, this is an independent set, and I have a complete bipartite graph between the guards and v1. Okay? So now notice that if I pick a vertex in v1, then I dominate all of the guards. However, if I do not pick anyone in v1, then I have to pick all of the vertices in v1 into my independent dominating set. All the vertices of the guards, yes, sorry. So if I do not pick any vertices in v1, then I have to pick all of v1's guards into the independent dominating set. Okay, so in particular, either there exists a clique, in which case here I can find an independent dominating set, or there isn't, which means that in any solution, for at least one of my vertex sets, I needed to have picked all the guards, and the ratio between the number of guards and k, I can make that as big as I want. Yeah. So, in particular, if G has a k-clique, then I have an independent dominating set of size at most k. If I don't have a k-clique, then then the size of the minimum independent dominating set is infinite. A good approximation, or actually a terrible approximation algorithm, can still distinguish between the case of having a k-clique and not having one. Okay, so that is the easiest FPT inapproximability result there is. All of the other ones are significantly harder for a reason, because we really used in the hardness of approximation here that the problem isn't monotone. Like, you can pick a vertex into your solution, and picking that vertex into the solution could be a terrible mistake because it forbids you from picking some other vertex that was really important that you did pick. Yeah? So any approximation algorithm sort of has to make sure that it doesn't make such mistakes, right? Whereas, for example, for dominating set, you pick some vertex into the solution, the worst thing that could happen is that you picked a lousy vertex that isn't doing anything. Okay, so you paid 1, and you got nothing for it, so you overpaid 1. All right, I mean, that's not terrible, right? So in this setting, it is much harder to prove hardness of approximation. So without further ado, let me go to the gap ETH and how we can use the gap ETH in order to prove hardness of approximation. So before we go to the gap ETH, let me remind you of what the ETH says, so the exponential time hypothesis. So this states that there exists some epsilon greater than 0 such that there is no 2 to the epsilon n algorithm for 3-sat, where n is the number of variables. Now, because 3-sat instances can have a bunch of clauses, just ETH by itself isn't terribly useful for reductions, because you end up, most of the time when you reduce from sat to something, then the number of vertices you have is the number of variables plus clauses in your original instance. And therefore, this fantastic tool called the Specification Lemma, which says that ETH is in fact equivalent to ETH prime, which is that for every epsilon greater than 0, there is no 2 to the epsilon n plus m algorithm for 3-sat. So now even the clauses can be in the exponent. So when you're reducing from this is much more useful. Okay. Another way to put ETH prime is to say that even 3-sat instances where every variable appears in a constant number of clauses for some constant, there is no 2 to the epsilon n algorithm. This doesn't immediately follow from what I wrote on the board, but the Specification Lemma actually proves that. Okay, so now let's define gap ETH, which is related to the ETH. And now, for that, I need to define this ratio max sat of a formula phi. So suppose I give you a CNF phi with n variables and m clauses, and then I go over all assignments to the variables, and then I see how many variables are satisfied how many clauses are satisfied compared to all of the clauses. Is it half the clauses? Is it 0.75 of the clauses? Is it all the clauses? Okay? So notice that a formula phi is satisfiable if and only if max sat of phi is equal to 1, right? If you can satisfy all the clauses. Okay? And for any CNF, the max sat is between 1/2 and 1, because in expectation, even when you have clauses of size 1, a random assignment is going to satisfy at least half the clauses. Right? If your clauses are bigger, your expectation is actually even higher. Okay. So, any questions with the definition of max sat of a CNF? No? Okay. So, now the next we're going to define the gap problem, epsilon gap version of 3-sat. So here input is a 3CNF, and the job of the algorithm is to do the following. If the CNF is satisfiable, you should say, yeah, it's satisfiable. If there is no way to satisfy more than a 1 minus epsilon fraction of the clauses, so if no matter how you set the variables, at least an epsilon fraction of the clauses will stay unsatisfied, then you should say, no, this formula is not satisfiable. Okay, now what should you do in the parts that I haven't defined things yet? So what happens for formulas where you can satisfy more than a 1 minus epsilon fraction of the clauses, but you can't satisfy all of them, you can answer yes, you can answer no, you can draw an elephant, you can crash, you can do whatever it is you want. Okay? So you only should say yes on satisfiable clauses, and you should say no if you cannot satisfy even a 1 minus epsilon fraction of the clauses. Okay? Is this clear?
In which time?
This is just a definition of a problem. Yeah. So far this is just a problem. Then the hypothesis will be what is the time. Okay. Okay. So now, see, now comes the problem. The gap ETH. This is a hypothesis formulated by Deneur in 2012 that for every there exists a tiny epsilon, but constant epsilon, greater than 0, and a delta greater than 0, such that there is no 2 to the delta n time algorithm for epsilon gap 3-sat. So in particular, there exists an epsilon such that distinguishing between satisfiable formulas and formulas that are 1 minus epsilon unsatisfiable, or like where you only can satisfy almost everything, but not quite, that distinguishing that cannot be done in sub-exponential time. So that's the hypothesis. Okay? Now, if we wanted to start doing reduction from this, of course we would still need a specification lemma. Because reducing from this is sort of useless. You still potentially have a lot of clauses. So we would like to instead to formulate gap ETH prime hypothesis, just like gap ETH, where now you have an m in the exponent instead. Yeah, m plus m. And just as for ETH, there is a specification lemma that says that gap ETH and gap ETH prime are actually equivalent to each other, at least for randomized algorithms. Okay? So from now on, whenever I say gap ETH or gap ETH prime, I'm always going to mean randomized for randomized algorithms. Okay, so whereas actually, so the interesting thing is that the specification lemma for ETH doesn't actually apply here, but the much easier argument applies for a specification lemma for gap ETH than for ETH, incredibly. Because if you're not trying to maintain satisfiability and exactly, you're allowed a little bit of a fudge, then you can have more simpler arguments. And here, so in order to prove a specification lemma for gap ETH, what is it you need to do? You need to make an algorithm that, given an instance of epsilon gap 3-sat with n variables and potentially many clauses, as many as n cubed, outputs an equivalent instance with order n variables and order n clauses. Yes? That's our goal. Okay, so that's what we're going to do now. And what we're going to do is the following. We're going to cleverly pick some constant c. Okay? And we're going to have n variables and c times n clauses in our new formula. And the way we're going to build our new formula is that we're just going to sample c times n clauses from our input formula uniformly at random and keep those. Okay? And incredibly, like with a simple, but I still won't show it here, but trust me, it is really simple, application of Chernoff bounds and then the union bound, you can show that with high probability, the maximum number of satisfied clauses, like the maximum ratio of satisfied clauses in the new formula minus the maximum number of satisfied clauses in the original formula is less than 1 over c. Okay? So in particular, notice that if phi is satisfiable, then phi prime is also satisfiable. Yes? And if phi was 1 minus epsilon unsatisfiable, then if I pick c so that 1 over c is less than epsilon over 2, then phi prime is going to be 1 minus epsilon over 2 unsatisfiable, so I still have an epsilon over 2 gap. Okay? And that's actually it. That's there's no more, not more to it than that. And in fact, you actually prove something stronger. We're not just, because we're using Chernoff and the union bound, we're not just proving that the maximum satisfying assignment is close to, in value, to the maximum satisfying assignment of the original formula. You're actually proving that this difference is small for every assignment to the formula. So for every assignment to the formula, the ratio of clauses that it satisfies is close to the ratio of clauses that it satisfied in the original formula. And close means differs by at most 1/c. Okay? So here is, so now we prove that ETH in fact is equivalent to ETH prime. Furthermore, nothing in our argument used the number 3, that our clauses have size at most 3. So whatever we did works just as well for max sat. Okay? And so when you have CNF clauses of arbitrary clause lengths, so in particular this proof of ETH is equal to ETH prime happens to be a 1 plus epsilon approximate kernel for max sat parameterized by the number of variables. Yeah. So you can sit down and if you remember the definition of lossy kernels, you can check that that is actually what it is. Which is interesting because sat parameterized by the number of variables does not have a lossy kernel. Yes? And that's does not have a kernel in the usual sense, and that's the very first no kernel result by Fortno and Santanom. Yeah? Whereas maxsat actually does now have one of these, which is nice. So that's all lossy kernels I'm going to talk about. MSR in the next talk gets to pick up the baton. So here's a minor annoyance, which is a difference between gap ETH prime and ETH prime. So in ETH prime, just normal exponential time hypothesis, we could assume that you cannot have sub-exponential time algorithms for 3 sat instances where every variable appears in a constant number of clauses. And here I wrote something wrong. Where is my pen? All right. So actually, this, okay. No, this, I won't be fixing it because I can't plug the pen in without destroying the projector. Okay, so this thing here should be gap ETH. So notice that if initially you started out with many clauses, you picked a random subset of them, you're actually expecting some of your variables to appear in, say, log n clauses. Whereas in normal ETH, every variable ended up appearing in a constant number of clauses. However, this is in fact just a minor annoyance. Let's formulate gap ETH star, which is another equivalent variant of gap ETH. And this is that there exists an epsilon and a delta, and a maximum degree, big delta, so that there is no 2 to the little delta n, so no sub-exponential time algorithm for epsilon gap 3 sat where every variable appears in at most delta number of clauses. And you can prove that this gap ETH star is actually equivalent to gap ETH. I'm not going to do this, but the trick is nothing but replacing every variable by a sufficient expander. Okay, so that's all I'm going to say about that. If you didn't understand that, then just believe me, it's a minor annoyance. Okay. So now that we have this wonderful tool, the gap ETH, in fact the gap ETH star, that if I give you a 3 sat where every variable appears in a constant number of clauses, potentially a large constant, then I cannot, in sub-exponential time, distinguish between satisfiable formulas and ones where at least an epsilon fraction will stay unsatisfied no matter what I do. So assuming this, I would like to prove some parametrized hardness. Before proving some parametrized hardness, let's do this sort of things that we did with ETH and prove some like 2 to the little o of n hardness for some other NP-complete problems. Yeah, that is like really the first exercise to do with ETH, so it's also the first exercise to do with gap ETH. In particular, let's define for a graph G max 3 coloring of G. So now, normal 3 coloring, I want to color every vertex with colors 1, 2, and 3 so that every edge has differently colored endpoints. Okay? In the max 3 coloring, I now want to maximize the number of edges that are happy. Yeah, where an edge is happy if it has differently colored endpoints. Okay? So I just define max 3 coloring of G to be maximum over all colorings of G of the number of edges that get properly colored divided by the number of edges. So again, this is a number between 0 and 1. Yeah, and you want... So just as for SAT, we can define a gap version of 3 coloring. So input is a graph, and you're supposed to say yes if the graph is 3 colorable. You're supposed to say no if no matter what you do, an epsilon fraction of the edges remain unhappy, get the same colored endpoints. And if the maximum number of edges that you can properly color is more than a 1 minus epsilon fraction, but not everything, then again you can do whatever. Okay? So now I will check whether you have been paying attention. And I'm going to check it in the following way. Please, assuming gap ETH star, prove that there exists an epsilon and delta so that there is no 2 to the delta n algorithm for epsilon gap 3 coloring. In other words, that you cannot do, there exists an epsilon, so you cannot do epsilon gap 3 coloring in sub-exponential time. You have 20 seconds. Okay, so any ideas?
Lexical reduction from which we got it.
Yes, so in particular, the correct answer is just do the reduction from NP completeness. So do Sipser's reduction from SAT to 3 coloring, and notice the fact that you are reducing from epsilon gap 3 SAT, where every variable appears in a constant number of clauses, and you're fine.
So I need both of it, right? I need the fact that there are not too many clause gadgets, which is why I need the
Yes.
classification for free, and then I need the degree bound because the clauses will connect to the color.
Yes, that's right. Actually, there is a minor annoyance here too. Okay? And the minor annoyance is the following, that in this reduction, you're making a palette. So you're making 3 vertices that are like true, false, and something. And in that reduction, they end up having some gigantic degree, and if you're not careful, there's all sorts of pain that can happen. However, in particular, you have a clique of size 3, right? And you want to color, and you're saying this is your palette because they get colored with different colors, right? Like true, false, and something. But you could now color the 3 of them true, true, true. And then you're in trouble for the rest of it. So actually, you have to do in the normal NP completeness reduction for 3 coloring and replace each of these 3 vertices in a palette with a linear size expander graph. Okay, whatever. But morally, it's the same thing. Okay? Okay, so finally, we have arrived at the promised land. Namely, we're going to, assuming the gap ETH, prove that there is no FPT approximation for clique. I was promising you any constant factor, but first we're just going to prove 1 plus epsilon. Okay? So there exists an epsilon, so there is no FPT 1 plus epsilon approximation algorithm for clique. That's what we're going to prove. Okay? And the way we do this is reduce from epsilon gap 3 coloring in the same way that you reduce to clique from 3 coloring, except that there are some minor annoyances. Okay, so let's handle those. So how do we do this? So we want to reduce from epsilon gap 3 coloring, and we want to make a clique instance, a k-clique instance, so that the output graph has a k-clique if and only if the original graph could be 3 colored, and a 1 plus epsilon k-sized clique should give you a coloring of the vertex sets that satisfies 1 minus epsilon fraction of the clauses, or of the edges of the graph. Okay. So the first thing we're going to do is we're going to split our graph into k groups, each of size n over k. And now we need one more additional property, and this is that between every pair of color classes, I want to have roughly the same number of edges. So for technical reasons, that ends up being useful. So anyone who can tell me, and where roughly I mean, well, there are, let's see. Now I'm also going to give away how to do it. If I color my vertices at random with colors from 1 to k, yeah, then with good probability, all of my color classes now have size very close to n over k, and the number of edges between any pair of color classes is like, okay, so the expected number is 2 divided by k square, and with high probability it's 2 divided by k square times m, where m is the number of edges, and with high probability it's that plus some sublinear terms. Yeah.
Using coloring in 2 different senses now, right?
Yes, so now I'm using partitioning. Okay, yeah. So now coloring was the partitioning, and from now on coloring will be coloring, and now I'll be using partitions. Okay, thanks. Okay. So now what do we do once we have partitioned our graphs into k parts? We're going to make a vertex for, yes?
Do you claim that there is such a partition?
Yes, in particular, pick one at random. It is like that with high probability. Yeah. Yeah. We're doing random. We're reducing from randomized ETH anyway, so randomized productions are fine. Yeah. Okay. So now what we're going to do is for all of the proper colorings of G induced by the first part, I'm going to make a vertex. There's 3 to the power n over k of those at most. For all of the proper colorings of V2, I'm going to make a vertex. Again, 3 to the power n over k of those, and so on, each for my k parts. And I'm going to put an edge between 2 vertices. Now, this corresponds to a coloring of V1. This corresponds to a coloring of V2. If there isn't any edge between a vertex in V1 and a vertex in V2 that gets badly colored, or like colored with the same colored endpoints, by these 2 colorings, then I put an edge. So like if these 2 colorings are completely consistent with each other with respect to coloring everything, yeah, then I put an edge. Okay? So all that remains to do is an analysis. And this is the following. Well, first, the total number of vertices in my output instance is k into 3 to the n over k. Okay? Now, if G is 3 colorable, then I have a k-clique. Well, just like take the vertex in every part that corresponds to that part of the coloring, and they're always vertices and they're pairwise consistent, so you have cliques. Great. Now, suppose that G prime has a k into 1 minus epsilon clique. I actually claim that G has a 3 coloring, making a 1 minus epsilon squared m edges happy. So why is that? So it's better to, like a picture says more than words here. So suppose my clique here was V1, so picked one vertex from each of these classes. I mean, the images of those classes, right? I mean, okay. So you picked so each of these classes now gave rise to these classes. So now let's pretend that in this picture, these are actually now classes in the graph G prime, rather than in G. Okay, so I'm going to use the same picture for two different graphs so that it won't be confusing. Okay. Okay, so now we pick the clique from the 1 minus epsilon k first color classes. Okay, so in particular, if I just pick the coloring of those color classes corresponding to the clique vertices, and then I color the rest with garbage. I just give color 1 to everything. This is this corresponds to a 3 coloring of my original graph. And if I look at the graph induced by the 1 minus epsilon k first color classes, that has been properly 3 colored. Because every vertex corresponds to a proper coloring of the part, and between every part the 2 colorings are consistent. So now all you need to check is what proportion of the edges are properly 3 colored. Yeah. And now we ensured that the number of edges inside each color class and between every pair of color classes is the same. So in particular, it is because I picked 1 minus epsilon fraction of the color classes, I'm covering a 1 minus epsilon squared fraction of pairs of color classes. Yep. So that gives us this, right? So in particular, if I have a f of k n to the little o of k time 1 square root of 1 plus epsilon, so basically like 1 plus delta approximation for clique, well, then it gives us an f of k times 3 to the n over k times little o of k, so that simplifies to 3 to the little o of n time 1 plus epsilon approximation for 3 coloring. Yeah, so we can't have that, assuming gap PTH star. Okay, so now we have a 1 plus epsilon in approximability result for clique. I promised you a constant factor in approximability for clique. And we can do this using a construction that Daniel Marks showed 2 talks back for a completely different application, namely this categorical product that he was saying. Okay? So in particular, if I have a graph, G, and I take the categorical product of G with itself, you can prove that the clique number gets squared. If you take it with itself 3 times, then the clique number gets cubed, and so on. Okay? So in particular, there is a construction that, given an n vertex graph, produces an n to the t vertex graphs for any constant t, such that max clique of the new graph is the original max clique to the power t. Okay? And now, because we know that either max clique was k or 1 minus epsilon k, now what we get is either k to the t or 1 minus epsilon to the t. We can now get an arbitrarily large gap between the yes and the no answers. So that's how you rule out any constant factor approximation in FPT time. Notice, of course, that here, because you are squaring things, k goes now to k squared, to k cubed, and so on. So that's why you don't get such tight results like for what you can do in n to the little o of k, but playing around with the order of when you amplify gaps and such, and how you amplify the gaps, you can do this. Okay, so that concludes the technical part of my talk. I have a little last remark that is important, and this is that many results in parameterized complexity that show W1 hardness or W2 hardness are actually parameterized reductions either from clique or dominating set, which we now just proved to be very FPT inapproximable. If your FPT reduction that you used to prove W hardness happened not only to be a parameterized reduction, but also an approximation preserving reduction. It seems that, like, most of the time when a reduction is simple enough, so in particular, my impression was that many of these computational social choice things that we're reducing from hitting set and dominating set, my guess is that they're actually FPT approximating. So many reductions, if you stare at them, you realize it's not only a FPT reduction, it's actually a approximation preserving FPT reduction. And then it actually shows that your problem is not only doubly hard, it's also hard to FPT approximate.
So this, and the thing you just showed us was if you want just the standard FPT reduction that you need to infer that K-clique is doubly one hard based on 3 coloring on ring TH.
Yes?
So and the extra spice you added here was merely the fact that there was a partitioning where you could bound the number of edges between the parts. Was that?
Yes, yes, that was the only spice.
And if you can do something like that, then this gives you a general. Okay, fine.
Yep, okay.
Thank you.
No, so in fact, now that you have strong inapproximability of clique in dominating set, the reductions from clique in dominating set to your problem, maybe they are already approximation preserving, or you can make them with a little bit of spice, and then you get inapproximability results on the go. Now, I wanted to, let's see, do I have time? So I want to point to a nice open problem that I don't have slides for. Namely, let's see. So here is a very nice open problem that we don't know. Okay. Unfortunately, I can't draw and show it at the same time. Oh, okay. Let me try here. I have I have an idea. Don't. Let's see. No, this, but I'm on flight mode so that like I don't get inappropriate messages while giving the talk. But now I turned on Bluetooth.
So if you're not in flight mode, you get inappropriate messages.
Of course.
I'm not judging.
All right, let's see. Yes, this works. All right, so now I'm in flight mode and Bluetooth is on. So if you want to send me inappropriate messages, you have to do this via Bluetooth. All right, here we go. Move down. Okay, so let me show you what problem I'm talking about. So consider the following problem. I give you a graph G. So this is my input. I give you a graph G with k vertices. So input is a graph G with k vertices. And every vertex corresponds to a variable. Okay? Now what are the values that these variables can take? They can take any number between 1 through n. Okay? So for every vertex, I need to set them to some value between 1 and n. Okay. Another thing I know about my graph is that the degree is at most 3. Okay? Now, every edge in my graph is a constraint. Okay? And what does it mean that it is a constraint? I'm just going to tell you the set of legal pairs of numbers. So set of legal number pairs that I can set these vertices to. So for example, I can say if I can set this guy to 1, 2, 3, 4, and this guy I can set to 1, 2, 3, 4, then maybe this edge is happy if I set this guy to 1 and that guy to 2, or if I set this guy to 1 and that guy to 5, or if I set this guy to 2 and that guy to 3, you get the gist, right? So I just give you the list of all pairs of assignments to those two variables that would make this edge happy. Okay? Now the task is maximize the number of happy edges. Okay? So clearly you can do this in time n to the k, right? You can just guess for every variable what to set it to. Okay? And now we're considering the following problem. It's the Epsilon Gap Variant. You want to distinguish between the instances where you can satisfy all constraints and the instances where every assignment unsatisfies at least an epsilon fraction of the constraints. Okay? And my conjecture is that epsilon gap, now I'm going to call this 2CSP, because this is constraint satisfaction where every constraint is on 2 variables, but the domain size is not 2. So like whenever you have some number CSP, it's always confusing whether it is about the arity of the constraints or the size of the domain. But this time it's the arity of the constraints. Okay? So epsilon gap 2CSP parametrized by the number of variables is W hard, or W1 hard, yes? So it is very easy, it's a nice exercise, to show that assuming gap ETH, there is no FPT algorithm that distinguishes between instances that are in fact satisfiable and the ones that are 1 minus epsilon satisfiable. But I believe that you can actually prove that assuming FPT not equal to W1, that you can prove that such an FPT approximation doesn't exist. In fact, if you prove it, so if you prove that this problem is W1 hard, this is actually equivalent to showing that every problem in W1 admits a certain kind of PCP. So if you're interested in that, you can come talk to me. I'll explain that. I think with that, let's say thanks.